Welcome back to AI Paper Podcast. Today we're going deep
yeah.
into Transformer², self-adaptive LLMs.
Ooh.
This paper has been making some pretty big waves.
Yeah.
With its approach to fine-tuning.
Right.
They're calling it self-adaptation.
Yeah, it's a pretty fascinating idea.
Yeah.
The main idea here is to kind of move away from those limitations of traditional fine-tuning.
Like,
you know, where you're basically retraining the entire model for each new task.
Yeah.
And they're kind of drawing inspiration from, you know, how our brains work.
Oh, interesting.
Focusing on activating specific regions.
Oh, cool.
For different tasks.
So it's like our brains aren't constantly rewiring themselves.
Exactly.
Every time we learn something new.
Yeah.
Got it.
They're kind of adapting by using existing pathways and connections.
Yeah.
And that's really the beauty of Transformer.
Right.
It's designed to mimic that adaptability. So it uses this two-step process where it first analyzes the input to figure out what kind of task it's dealing with.
It's like an assessment phase.
Exactly, like a quick assessment. And then in the second step, it combines these pre-trained expert vectors to tailor its weights for that specific task.
So almost like...
It's like having a cool box full of specialized tools, and the model knows which one to pick up based on the job at hand.
I'm starting to see how this could be a lot more efficient.
Yeah.
But how are these expert vectors created in the first place?
That's where SVF comes in.
Okay.
Singular value fine-tuning.
Right. The paper mentioned that.
It's a parameter-efficient fine-tuning method that basically modifies only the singular values of weight matrices.
Okay.
Now, I don't want to get too lost in the weeds of linear algebra here.
We don't have to go down that rabbit hole.
But the key takeaway is this. SVF allows the model to adapt without needing to learn tons of new information, making it far more efficient.
So more efficient
than traditional methods.
Got it.
Yeah.
So instead of giving the model a whole new textbook,
exactly,
you're giving it like a specialized lens.
You got it.
Okay.
It can focus on specific aspects of a task without having to relearn everything from scratch.
That's brilliant.
And there's more.
Oh, there's more.
Because SVF focuses on singular values. The resulting expert vectors are incredibly flexible. You can combine them in various ways to tackle a wide range of tasks.
So it's really composable.
It is. It's that composability that makes the system so adaptable.
Now we're talking serious efficiency and flexibility.
Exactly.
Every AI researcher loves to hear.
That I'd love to hear, yeah.
Absolutely.
But how do you actually train these SVF experts? How do we know they're actually good at their specialized tasks?
Right.
The paper mentions using reinforcement learning.
Yeah, that seemed a bit unusual to me.
Yeah, it's not the typical supervised learning approach.
Okay.
They use reinforcement learning to directly optimize those experts for task performance.
Okay.
Essentially, they're training the model to perform specific actions and rewarding it when it succeeds.
Makes sense.
They use the reinforce algorithm and they incorporate something called a KL penalty term.
KL penalty.
Regularization.
Okay, now for those of us who haven't brushed up on our RL theory, could you break that down?
Sure. Think of it as a safety net.
Okay.
The KL penalty keeps the model's behavior aligned with the original pre-trained model, preventing it from going rogue.
So it doesn't forget everything it learned before.
It prevents it from forgetting its core knowledge while learning these new tricks.
Got it.
It's a crucial part of why they can train on smaller data sets without overfitting.
So it's like giving it some guardrails as it explores these new...
Precisely. This combination of reinforcement learning and that KL penalty allows them to achieve really impressive performance with much less data.
I like it. Less data is always good.
Yeah, it's a huge win in the world of LLMs.
A huge win, yeah.
Absolutely.
All right, so we've got these specialized experts.
Right.
They're trained with this really clever SVF technique and then refined through reinforcement learning.
Exactly.
But how are they actually used at inference time?
So
You mentioned the model figures out which expert to use.
Yeah, that's where their adaptation strategies come into play.
Got it.
They've outlined 3 different methods for dynamically combining these SVF experts.
Okay, let's unpack these strategies.
At inference time.
Yeah, what's the first one?
So the simplest approach is prompt engineering.
Okay.
It's all about crafting the input prompt in a way that guides the model towards selecting the right expert.
So you're kind of baking the task selection into the prompt itself.
You're giving it a gentle nudge in the right direction.
How well does that work?
So it's surprisingly effective for simpler tasks.
Right.
But as you can imagine, there are limitations
I can imagine.
to how much information you can pack into a prompt.
Makes sense.
And that's where the second strategy, the classification expert, comes in.
So instead of relying on this cleverly worded prompt, you're bringing in a specialist.
You got it.
Okay.
They train a dedicated SVF expert specifically to classify the task.
Okay.
It analyzes the input
and
determines which expert from the pool is best suited for the job.
So it's like...
This leads to significantly better accuracy in matching the prompt with the right expert.
Like a triage nurse in the ER.
Exactly.
Sending people to the... specialist.
Exactly.
I like it. What about the third strategy?
So the third strategy...
Few-shot adaptation.
Few-shot adaptation.
Yeah.
This one really showcases the power of learning from minimal examples.
Okay.
Imagine giving the model just a handful of examples from the new task. And it figures out how to combine its existing experts to solve it.
That's impressive.
It's really remarkable.
But how does it do that?
So they leverage something called the cross-entropy method, or CEM, to search for the optimal way to blend the different experts' knowledge.
So basically, they're experimenting.
Essentially, they're rapidly experimenting with different combinations of experts. Figuring out which blend leads to the best performance on those few examples.
Okay, now I'm really curious to see how this performs in practice.
Did they put it to the test?
Did they actually test Transformer?
Absolutely. They did a very comprehensive set of experiments comparing Transformer with other state-of-the-art fine-tuning methods. Like LoRA. Across a range of tasks. From math problem solving to code generation reasoning and even a vision language task.
That's quite a range.
It is. It's a pretty diverse set.
So what were the results?
The results are quite compelling.
Okay, good.
Across the board. SVF consistently outperformed LoRA.
Okay, so it lived up to the hype.
Yeah, achieving better performance with significantly fewer parameters.
That's a big win for singular value.
And remember, fewer parameters means greater efficiency.
Yeah, absolutely.
Which is a huge win.
Huge win.
Yeah.
What about the different adaptation strategies? How do they do on unseen tasks?
So they specifically tested Transformer on 4 challenging tasks. Math, Humanivol, ARC challenge, and OKVQA.
Got it.
What's interesting is that all 3 adaptation strategies demonstrated improvements over baseline models.
Oh, wow.
Particularly in tasks like math and Humanivol, where traditional fine-tuning methods struggled.
So even just prompt engineering.
Yeah, even the simplest strategy.
Give it an edge.
Gave the model a noticeable edge.
Interesting.
Exactly.
What about as you move towards...
But as you move towards more sophisticated strategies, the performance gains become even more pronounced. The trend is clear. The more information the model has about the task, the better it can adapt.
Makes sense.
Not perform.
Okay, color me intrigued, but I'm a show me the data kind of person. What kind of analysis did they do?
So they didn't just focus on those top line results. They delved deeper. They analyzed things like the accuracy of job dispatching, which tells you how well each strategy matched the prompt to the right expert.
Got it.
As you might expect, both the classification expert and the few-shot adaptation methods were significantly more accurate than relying solely on prompt engineering.
So having that expert or a few examples?
Yeah, it makes a big difference in guiding the model towards the right skill set.
What else did they explore?
They also investigated how much each training task contributed to the model's ability to adapt to unseen tasks. And this is where things get really interesting. Because the contributions weren't always intuitive. For example, in some cases, the expert trained on a reasoning task proved more helpful for solving a math problem than the expert trained specifically on math.
So there's some implicit knowledge transfer.
Exactly. There's a deeper level of understanding and generalization. They also conducted ablation studies to test the robustness of SVF.
So like a controlled...
Yeah, systematically removing different components of the model.
Right, to see which parts were essential.
To see how it affected performance.
Yeah, got it.
And the results were encouraging.
Okay.
SVF proved to be quite robust across different configurations, suggesting that it's not overly sensitive to specific settings or hyperparameters.
So it's a strong core design.
It is. It's a testament to the strength of the core design.
All right, we've covered a lot.
Yeah, we have.
Impressive results.
Absolutely.
Thorough analysis, robust design.
Yeah.
But was there anything that really, surprised you?
There was one finding that really caught my eye.
Oh, okay.
And it has significant implications for the future of LLMs.
Right.
They discovered that SVF experts trained on one LLM could actually benefit another LLM.
Wait, hold on. So they're transferable?
Yeah, even across different model sizes.
That's huge.
It is.
Wow.
And to confirm it wasn't a fluke, they shuffled the order of the singular values, and the performance dropped significantly.
So that structure is really important.
Yeah, this suggests that the structure of SVF, its reliance on singular value decomposition, is key to making this cross-model transfer possible.
This could change how we develop.
It really could.
And share models.
Absolutely.
Imagine having libraries.
It's like open sourcing expertise for AI.
Of these pre-trained experts.
Exactly.
That you could just plug and play into different LLMs.
That's the exciting potential here.
Yeah.
It opens up new avenues for collaboration and knowledge sharing.
So we could move away from training these.
Yeah, we could see a shift
models.
From training these massive monolithic models to developing more specialized and adaptable ones.
And that would be a lot more efficient.
Fostering a more modular and efficient approach.
Okay, so we've gone really deep into the details here.
We've gone deep.
But let's step back for a second and talk about what this means for our listeners.
Right.
You know, the AI researchers and the ML engineers.
Yeah, the folks out there on the front lines.
What are the key takeaways?
So this paper paints a compelling picture of a future where LLMs are no longer these static, one-size-fits-all behemoths.
Yeah.
Instead, we're talking about dynamic systems that can continuously learn and adapt to new challenges.
Like a Swiss Army knife.
It's like a Swiss Army knife of AI.
Of AI, yeah.
Yeah.
Yeah, that's awesome.
Imagine LLMs that can seamlessly switch between being an expert coder, a mathematician, a creative writer, a data analyst,
and more.
All within the same model.
Yeah. The possibilities are pretty mind-blowing.
It is. It's pretty mind-blowing.
But let's play devil's advocate for a second. Are there any limitations?
Of course. There are always limitations and challenges to consider.
Okay.
One thing the authors acknowledge is that the capabilities of these SVF experts are still bound by the knowledge present in the base LLM.
So if the base model doesn't know it.
If the base model doesn't have a certain skill, the experts can't magically create it out of thin air.
Got it. Okay.
Yeah.
So it's not a complete replacement?
It's not a complete replacement.
For fine-tune?
For traditional fine-tuning.
We still need to start.
We still need to make sure.
The really base models.
Good base are as comprehensive and capable as possible.
Yeah. Okay. What about efficiency?
Right.
You know, few-shot adaptation sounds great.
Yeah.
But could it get really expensive?
That's a valid concern.
Computationally, yeah.
Scaling this approach to a massive number of specialized domains could introduce some computational overhead.
Especially during inference.
Especially during inference, yeah. However, the authors do suggest several potential solutions, such as exploring more efficient search algorithms or developing smarter methods to pre-select the most relevant experts.
Makes sense.
For a given task.
Were there any other?
So there are optimization opportunities to explore, which is always exciting for researchers.
Always exciting. Any other potential downsides?
Well, it's important to remember that this is still early days for self-adaptive LLMs.
Okay.
This paper primarily focuses on the inference stage, but there's a lot more to explore in terms of how these models could learn and evolve.
So it's like we've opened this door.
Exactly.
But we've only just started.
We've only just begun to explore its vast landscape.
I like it.
And the authors hint at some fascinating directions for future work, for instance. They mentioned the potential of combining self-adaptation with model merging techniques.
Oh, interesting.
Imagine merging multiple specialized LLMs into a single model that can dynamically activate.
That could be super powerful.
The most relevant parts for a given task.
Yeah.
We're talking about a whole new level of flexibility.
Now we're getting into truly self-organizing AI.
Exactly.
It's a concept that was once science fiction.
Right.
But now it's almost here.
It seems tantalizingly close.
Yeah.
And that's what makes this research so compelling.
It's really cool.
It is. It's pushing the boundaries of what we thought was possible.
Right.
With LLMs.
Totally.
And it's showing us that we can create AI systems that are more aligned.
That learn more like we do.
With how we as humans learn and adapt to new information.
I like it.
So this paper really paints a compelling picture of a future where LLMs are no longer these static, one-size-fits-all behemoths.
Yeah.
Instead, we're talking about dynamic systems that can continuously learn and adapt to new challenges.
Yeah, like a Swiss Army knife.
It's like a Swiss Army knife of AI.
Of AI.
Exactly.
That's awesome.
So imagine LLMs that can seamlessly switch between being an expert coder, a mathematician, a creative writer, a data analyst.
One more.
All within the same model.
Yeah, the possibilities are pretty mind-blowing.
It's pretty mind-blowing.
But let's play devil's advocate for a second.
Okay.
Are there any limitations to this approach?
Of course there are always. Limitations and challenges to consider.
Okay.
One thing the authors acknowledge is that the capabilities of these SVF experts are still bound by the knowledge present in the base LLM.
So if the base model doesn't know it.
If the base model doesn't have certain skill, the experts can't just magically create it out of thin air.
Got it. Okay.
Yeah.
So it's not a complete replacement?
It's not a complete replacement for traditional fine-tuning.
We still need to start with a really...
We still need to make sure that our base models are as comprehensive and capable as possible.
Yeah. Okay, what about efficiency?
Right.
You know, few-shot adaptation sounds great.
Yeah.
But could it get really computationally expensive?
That's a valid concern.
Especially during inference.
Scaling this approach to a massive number of specialized domains could introduce some computational overhead.
Especially during inference.
Especially during inference, yeah. However, the authors do suggest several potential solutions.
All right.
Such as exploring more efficient search algorithms or developing smarter methods to pre-select the most relevant experts
makes sense
for a given task.
So there's a lot of room for optimization.
Yeah, there are optimization opportunities to explore.
Always exciting.
Absolutely.
Any other potential downsides that they highlighted?
Well, it's important to remember that this is still early days for self-adaptive LLMs.
Got it.
This paper primarily focuses on the inference stage, but there's a lot more to explore in terms of how these models could learn.
Right, so it's like we've opened this door.
Exactly.
But we've only just begun to explore.
We've only just begun to explore its vast landscape.
Yeah, I like it.
And the authors hint at some fascinating directions for future work.
Okay.
For instance, they mention the potential of combining self-adaptation with model merging techniques.
Oh, interesting.
Imagine merging multiple specialized LLMs into a single model. That can dynamically activate.
That could be really powerful.
The most relevant parts for a given task.
So now we're talking.
It's got a whole new level of flexibility and efficiency.
Now we're getting into truly self-organizing AI.
Exactly.
Yeah, it's a concept that was once science fiction, but now it's almost here.
Tantalizingly close.
Yeah.
And that's what makes this research so compelling.
Yeah, it's really cool.
It is. It's pushing the boundaries of what we thought was possible with LLMs.
Totally.
And it's showing us that we can create AI systems that are more aligned.
That learn more, like we do.
With how we as humans learn and adapt to new information.
I like it. It's an exciting vision, right?
It is.
It really is.
But it's important to remember this is still early days.
Yeah, for
self-adaptive LLMs.
Right.
This paper primarily focuses on the inference stage.
Right.
But there's so much more to explore in terms of how these models could learn and evolve over time.
So like we've opened this door.
Exactly.
But we've only just begun.
We've only just begun to explore its vast landscape.
Yeah, and the authors hint at some...
And they do. They hint at some fascinating directions for future work.
Okay, like what?
For instance, they mentioned the potential of combining self-adaptation with model merging techniques.
Oh, that's interesting.
Imagine merging multiple specialized LLMs into a single model that can then dynamically activate.
That could be really powerful.
The most relevant parts for a given task.
Yeah.
We're talking about a whole new level.
So now we're talking about truly self-organizing AI.
Exactly.
It's a concept that was once science fiction.
Right.
But now it's almost here.
It seems tantalizingly close.
It does.
And that's what makes this research so compelling.
It's really cool.
It is. Yeah. It's pushing the boundaries of what we thought was possible with LLMs.
Yeah.
And it's showing us that we can create AI systems that are more aligned.
But learn more like we do.
With how we as humans learn and adapt to new information.
It's been an amazing deep dive into Transformer².
Yeah.
Self-adaptive LLMs.
Absolutely.
I think we've uncovered some really groundbreaking ideas.
I think so too.
But before we wrap up, I want to leave our listeners,
of course,
the brilliant minds pushing the boundaries of AI.
Absolutely.
With a final thought-provoking question.
Okay, I like it.
We've discussed how Transformer uses these pre-trained experts. What if we could go a step further? What if these experts were able to learn and adapt on their own?
Right.
Becoming even more specialized.
Becoming even more specialized and efficient over time.
It's
a bold vision.
It is.
But one that seems increasingly within reach.
And I think that's what makes this research so compelling.
Right?
It is. It sparks these new questions.
New questions, new possibilities.
Yeah.
It challenges us to think beyond the current limitations.
Right.
And envision a future where AI is not just a tool, but a collaborative partner.
Like a partner in our pursuit.
In our quest for knowledge,
and
understanding.
Yeah, I love it.
It's exciting stuff.
So to all our listeners out there, keep those questions swirling.
Keep pushing the boundaries.
Keep pushing the boundaries.
Absolutely.
Let us know what you think.
We'd love to hear your thoughts.
We'd love to hear your insights, your ideas on this paper. Until next time.
Until next time.
Stay curious. Stay innovative.
Stay curious.
And keep exploring.
Yeah.
The ever-evolving world of AI.
The ever-evolving world of AI.